The title of my presentation is Temperature Features of Magnetic Resonance of Manganese 0.13, Mercury 0.87 Tellurium. Investigation was carried out at the Zavoysky Institute. The plan of my report is the following. I will speak about the motivation characteristics of the samples and our measurements. I will talk about our measurements on the APR technique performed at different temperatures. Semiconductors with variable band gap of impurities concentration are most used in the fabrication of infrared photodetectors. A popular compound is cadmium mercury tellurium. However, this compound has instability of the lattice, surface, and interface boundary. Alternative materials such as the manganese mercury tellurium and zinc mercury tellurium have a number of advantages that have been studied. These advantages include improved structural properties such as microhardness and dislocation formation energy, and fairly high mobilities of charge carriers, and eventually allow to replace cadmium mercury tellurium with them, especially in applications where stringent requirements are imposed on the stability of devices parameters. Now I will talk about that was investigated about magnetic properties of this compound. In accordance with the data of Adrianov, at 50 kelvins there is phase transition from paramagnetic state to the antiferromagnetic state. In accordance with the works of Brandt and Belaev, the manganese ions can form clusters. But in accordance with the data of Nagata, the antiferromagnetic exchange interactions is much less than the exchange interactions between the conductivity electrons and the spins of manganese ions. Despite the fact that these compounds have already found wide practical application, they continue to attract the attention of researchers due to the observation of quantum effects in them. Here are some recent demonstrations works, and these are work on the study of topological properties in quantum well, realization of the Weyl semi-metal state in manganese mercury tellurium, and the other magnetic topological insulators revealed manifestations of Majorana fermionics modes. All these studies can be considered within the framework of global problems of constructing qubits for quantum computers. Kren et al. Showed that in dilute magnetic semiconductors, circularly polarized light polarizes charge carriers, electrons and holes. In the process of exchange interaction between the manganese spins and the spins of the charge carrier. Here is the sample with the main type of carriers, holes. Holes are light and heavy. In the second work, it was shown that to oppose the magnetization, it is necessary that the concentration of charge carriers be sufficient for the formation of clusters. Shown here a model of polaron formed by a hole and localized on an acceptor. Let us consider the model of the formation of a magnetic polaron in more detail. From the experimental studies obtained earlier, it follows that the manganese ions interact in antiferromagnetic, and the constant of antiferromagnetic interaction is 0.8 millielectron-volts. The RAS, the antiferromagnetic interaction of a hole and a manganese ion, is much larger and equal to 360 millielectron-volts. That the hole rotates all the nearest manganese ions antiferromagnetically towards itself, and manganese ions form a ferromagnetic order. Main properties of this compound are well known, but the study of these crystals by magnetic resonance is new. Therefore, the aim of our work was to study the magnetic properties of manganese mercury tellurium monocrystals by magnetic resonance method, where mole fraction of manganese ions is 13%. Sample was grown by crystallization from two-phase mixture with replenishment of the melt from a tellurium solution. Electrophysical properties of our sample are shown in a table. Our sample is a narrow-gap semiconductor. Manganese tellurium compound has a hexagonal structure, and mercury halcogenate has a zinc blende structure. For small values of manganese concentration in manganese mercury tellurium, the distance between the manganese ions are large enough and cannot change the structure. So compound mercury manganese tellurium has a zinc blende structure as well. In general, the structure and the macroscopic homogeneity of the crystals is determined by the method of Grothendieck by impurity ion concentration. We may regard mercury manganese tellurium as a pseudobinary alloy of mercury tellurium and a zinc blende manganese tellurium. Manganese ions are dissolved in the diamagnetic matrix of mercury halcogenate. At a low concentration of manganese ions, the dipole-dipole interaction between their magnetic moments is small. The electron spin resonance spectra were recorded using ER200 SRC, a mix-plus spectrometer Bruker in X-band at the frequency of 9 GHz. Measurements were performed at the temperature from 5 to 100 kelvins, at the magnetic field varying from 0 to 14 kilorstad. From our previous scanning tunneling microscope measurements it was established: firstly, diffractogram showed that the crystal is a single phase. Secondly, that there are same dislocations in the crystal. And finally, the lattice period was estimated. Examination with an electron microscope made it possible to accurately establish the molar concentration of manganese ions. Average concentration of manganese ions 12.78%. However, here we see how the manganese ions are not uniformly located inside the crystal. Temperature evolution of the magnetic resonance spectrum is presented in a figure. As shown in a figure, The exchange narrowed line was observed due to all manganese 2+ ions and charge carriers. The SR spectrum was approximated by Lorentz by formula. The resonant field, line width, and amplitude have singularities in the range of 25-35 kelvins. Phase transition is observed near 30 kelvins, the nature of which is under discussion. The line intensivity is proportional to the amplitude of the SR signal, first derivative, multiplied by the square of the line width. The temperature dependence of the line intensivity was fitted by Curie-Weiss law. The Curie temperature was -35 kelvins. Conclusion. Investigations of the magnetic properties of the single crystals have been studied by SR methods. The strong exchange interaction between the spins of conduction electrons and manganese ions leads to the non-trivial behavior on the temperature dependence of the SR spectra of a single crystals manganese, mercury, tellurium with concentrations 0.13. Phase transition is observed near 30 kelvins. Curie temperature is -35 kelvins. We thank Nikolai Lyadov for the SEM measurements and Filip Milovich for the TEM measurements. Thank you for your attention.